Alan Turing was an English mathematician, computer scientist, and wartime codebreaker, considered by most to be the father of modern computing. He studied mathematics at Cambridge University, where his pioneering work in theoretical computer science first led to proof that automatic computation cannot solve all mathematical problems. This concept, known as the Turing machine, is considered the basis for the modern theory of computation. During the Second World War, Turing worked at Bletchley Park, where he played a vital role in deciphering messages encrypted by the German Enigma machine and developed new techniques for decoding messages on an industrial scale. A contribution that many believed helped shorten the war by more than 2 years and save an estimated 14 million lives. After the war, Turing was recruited by the National Physical Laboratory, where he designed the first complete specification for a digital computer. Had it been built, Turing's groundbreaking blueprint would have been vastly superior to any of the earlier computers at that time. In 1948, Turing joined Manchester University, where he directed the computing laboratory and developed a body of work that helped to form the basis for the field of artificial intelligence. Turing was prosecuted in 1952 for homosexual acts and accepted chemical castration treatment. He committed suicide in 1954. In 2009, British Prime Minister Gordon Brown made an official public apology on behalf of the British government for the appalling way he was treated. Queen Elizabeth II granted him a pardon in 2013. Ladies and gentlemen, welcome to tonight's Turing Talk, which has been held in partnership with BCS. Please give a warm welcome to your host for this evening.
Thank you and good evening, everyone. My name is Mark Birkin. I'm the Programme Director for Urban Analytics at the Alan Turing Institute. And it's my great pleasure to welcome you to this evening's event, A Day in the Life of a Smart City. We also have a virtual audience this evening watching elsewhere on YouTube, so a very warm welcome to all of you as well. Tonight we have two speakers for you, Aneni Bambara-Aban and Professor Julie McCann. There'll be a question and answer at the end of the second talk, so please do save your questions for the end there, with a good amount of time for that discussion. Again, if you're watching with us online, please do post questions in the chat box, and we can include those as well. So, a day in the life of a smart city. Smart cities, wired cities, innovation cities, connected cities, digital twins, urban analytics, a whole variety of terms, I think, capturing the variety, diversity, and excitement of the opportunities in this domain, which I would see as constituting data connected by data science, artificial intelligence, various other technologies. My own interest is, I've been interested for many years in urban simulation, connecting data, trying to understand how that data can be used to drive simulation and models, particularly to support policy intervention, planning, for all sorts of things, varying from transportation to retailing, crime, education and health. I think it's been one of the things that's been quite interesting for me over the last couple of years is the way that data has really come to the fore in conversations around the pandemic. For me, however, very much a mindset of a kind of a reactive approach to what the data can do for us. And I still like to see a lot more being done in terms of the interpretation of how that can support us in mitigation, in regulation, in positive strategies. And I say these things not because I expect them to be of very direct connection to some of the things that the speakers want to say to you this evening, but really just to make the point that I'm convinced that much of the excitement lies ahead of us in this kind of smart cities space. And I'm really looking forward, as I'm sure you are, to hearing the sorts of direction that Aneni and Julie are going to want to take us in relation to AI, robotics, algorithms, whatever it might be. So the first speaker this evening is Aneni Bambara-Aban. She's a multi-award winning robotics engineer and STEM communicator, she founded the TechOver Foundation, an international NGO focusing on encouraging, educating and supporting individuals from underserved communities into technology. Her most recent outreach program includes teaching girls from rural Nigeria how to build their first robot through sustainable and renewable materials. She's worked in multiple technology sectors and currently works as a product owner for an e-commerce tech startup based in Ghana, whilst on a scholarship postgraduate degree in data science at the University of West of England. Please join me in welcoming Anani onto the stage.
Hello, hi everyone. So grateful to be here, and I'm incredibly grateful to you guys for braving Storm Eunice and Storm Franklin. Today we are going to be talking about smart cities. We're going to prepare you for the lecture that Professor McCann has later. But I'm taking it from a different angle today. We're going to talk about smart cities, but building Wakanda, the feasibility of smart cities within Africa. Okay, so a bit about me. My name is Anani. I'm a robotics engineer and STEM communicator. I'm also the founder of the TechOver Foundation. So, we basically help young people get into STEM, into robotics, into coding. And I'm also the founder of the Anime and Chill community, which is a safe, inclusive community of nerds, basically. We like all things from anime to gaming, all of it. Why am I talking about that today? It's because our next topic is literally going to be about comics. Do we have any Marvel fans in the house? Any Marvel fans? Woo, okay. Any Black Panther fans? Yeah, Wakanda forever? Okay. Well, talking about Wakanda. Wakanda is a fictional country in East Africa. It does not exist, but Wakanda is very interesting because it was developed by, a comic book artist years ago. We're talking about 1966, I believe, it was first shown in Fantastic Four. And the fact that, this idea of a city as inspirational as Wakanda could exist, and somebody could think of that, it blows me away. Pictured here, we have Burning Zana. Burning Zana is located within Wakanda. It basically has maglev trains, which are trains that operate off magnetic force, and there's no cars, so basically everyone walks around. But the main thing here is it gives us a kind of image of what the future could look like when it comes to technologically advanced African cities. So at the moment, smart cities in Africa are becoming a bit more developed. We are seeing it pop up more in different countries, but there's still little known about the developments that are actually happening at the moment. Smart. So I'm sure you guys have heard this word said everywhere, like smart technology, smart living, smart this. But what does SMART actually stand for? Well, we know SMART to kind of stand for intelligence or the property of knowing something very well. But SMART is also a backronym for self-monitoring, analysis, and reporting technology. So in 1992, IBM actually made this. This was actually for SSDs, so state solid drives. And how it worked is before the drive would fail, it would let you know what was going on. Like there was some failure within it, and then you could actually, save your data before you lost everything. We can apply that smart knowledge today in in so many things. We have smart cities. We can apply that to how we live, how we move around, logistics. And I think it's important, before we talk about smart cities, to talk about urbanization. Because at the moment, the world's urban population is 4.4 billion people. That's more than the world's total population in 1975. More than half of the world's population now live in cities, and this is projected to expand to 2/3 by 2050. So urbanization is great, more people coming into cities, increases GDP. There's so many factors that come when you think about urbanization. But that also means increase in the carbon emissions, increase in energy used and wasted, and we need a solution to this, right? Smart cities is that solution. A smart city is a place where traditional networks and services are made more efficient with the use of digital solutions for the benefit of its inhabitants and businesses, as well as to address growing urbanization challenges. Say this a bit more simply, It's basically leveraging technology that already exists, so things that we use in our everyday lives now, and applying it to cities to make them more sustainable. So going back to Wakanda, Wakanda has vibranium. If you guys have seen the movie, you know vibranium does not exist. If it did exist, we'd be very happy. But no, vibranium does not exist. So we do have a few other resources that we can use that are just as good. In that capacity, we can do this by building cities from the ground up, or we can do that through retrofitting, which is essentially attaching sensors to pre-existing cities. So some features of smart cities. We have smart living, you know, having your kettle boil water before you get home. That's something that we can do right now through the Internet of Things. Something that seems so mundane, but a few years ago, this wouldn't have been possible. Smart education. VR systems that children can wear, especially in countries like Africa, in continents like Africa, where teachers are not, you know, maybe as qualified sometimes, or there's not availability of teachers to actually teach the students. You can have VR systems where teachers can be remotely teaching. You can have monitor screens in front of the class where the students are learning, and the list goes on. So pictured here, we have 4 smart cities. These are Switzerland, Zurich, Oslo, Norway, Taipei, Taiwan, and Lausanne in Switzerland. Singapore has actually been top 3 smart city in the world for the last 3 years. It has been top 1 smart city for the last 3 years. And honestly, Singapore got this down to a T very quickly. And I think they are the kind of the blueprint. They're showing other cities what they could do. They have everything from mobility, smart mobility. They have drones that deliver things so that you don't have to have cars on the road. They have e-governance, where people can directly speak to their government and tell them what they need or what they need done. But moving on to smart city initiatives in Africa. Bernin Zana from Wakanda has done a lot. You know, we can see how great it is fictionally. But in reality, what could the future look like for African countries? Let's start with Senegal. Do any of you know Akon? Akon is a very famous musician, and he's also an entrepreneur. He actually founded Akon City. He announced his plans in 2018 along with the Minister of Tourism for Senegal, and they've been trying to build their own version of Wakanda that works off solar power. It's inspired by Wakanda, and it's 2,000 acres of Senegalese coastline. So he did first share this project in 2018, and it's costing $6 billion. But we haven't heard much about what is going on with regards to Akon City. There are some factors which I'll discuss later which could potentially be hindering its development. But in 2021, he did announce that they will start building. We're still hearing, we're still waiting, not sure quite yet. Ghana. Ghana has the Wakanda City of Return project. This was launched in 2022 by the African Diaspora Development Institute, Cape Coast Metropolitan Assembly, and other local partners, Cape Group and Adepa Investment. Together, they are trying to build a place where people who are from Africa, who want to know more about their roots, who are maybe living in other continents and want to come back and learn what it is to be African, about their country specifically, can come there. And it's almost like a pilgrimage. So you come there, you learn about where you're from and about culture. So they've said plans are going to include 5G. They're going to have smart mobility. They're going to have smart living. There's going to be a resort which works off smart technology. We are yet to hear what's going to happen with that. There still has been no news on the progress of this project either. Then we move on to South Africa. This is Lanzaria. It's actually near an airport, so it's basically an aerotropolis. It was first conceptualized in 2007, but the President Ramaphosa has only just announced his plans in 2021 to make it the first, smart city that's going to be in South Africa post-apartheid. So here they're going to have infrastructure which is going to be connected with the airport being the main central point. Pictured here we have Konza, Techno City in Kenya, Kigali City in Rwanda, Mundafertin from South Africa, and Echo Atlantic, Nigeria. These are other smart city projects that are currently being worked on. A lot of them are going to be developed hopefully by 2030, but we still do not see a lot of progress. So although Africa as a continent is best suited for I guess, being a smart city and having smart cities, why is it that there still isn't much progress? Why are we not hearing about these things? I mean, from this, you can see there's an increase in middle class. There's more people moving to the cities. So that urbanization is increasing. And that works for us in this context because it means that the GDP of the countries will be going up. There's availability of natural resources in Africa. There's so much. There's from gold to oil. There's a necessity to tackle corruption and just a load of factors. But one that kind of reached out to me was the fact that we can use that data that we're getting from the sensors and from retrofitting in certain cities in Africa and work on things like traffic insights. So traffic. Lagos State, if you've heard of it, is one of the worst states when it comes to traffic in the world. Lagos has this traffic issue, but the traffic isn't so much the main problem that I saw when I actually went over there. It's the road accidents and the people that were getting injured and not being able to get close enough to the hospitals and to health centers because of the traffic. So this is how I came up with a project which would basically kind of get rid of that issue of traffic, being an obstacle to getting life-saving medication, and we could bypass that. So this is Makoko. Makoko is a riverine-based community in Lagos. In 2016, I designed and pitched a drone idea that would basically deliver medication from the local hospitals to the Makoko community so that they wouldn't have to go through all that traffic. So imagine you needed emergency blood supply and you'd just been in an accident, but you couldn't actually get to the hospital because the traffic, a 20-minute journey was taking 3 hours. Things like that should not be a factor for why somebody loses their life. So this drone was meant to solve that problem. So as you can see, it takes 42 minutes if you're meant to go. This is not even considering the traffic. If you're just going to go there, it was 42 minutes. Whereas with the drone, it takes 10 to 15 minutes for a 5-kilometer journey. But this is where I had a few issues. Pictured on the left, you have the Federal Ministry of Health in Abuja. So trying to go and pitch an idea such as a drone, which is, drones are used everywhere in the world. It's not a new concept or new technology. But trying to pitch to them why essentially this would be good to bypass that traffic issue, the main thing I realized is you have to have quite a progressive government. The government has to be on board. And unfortunately, with a lot of African countries, there is the factor of corruption. And unless you can actually bypass that and you can actually speak to people or speak to a government that's ready to make those technological changes, things do get a bit tricky. Next, I work with a private institution, which is called NACA, and they basically work with delivering HIV medication. So they were a lot more open to it, but again, when we came to actually implementing, we had the government level kind of blocking us from being able to do that. So this brings me on to what needs to change to make smart cities truly feasible. So just going off that, I'm definitely going to say the first thing has to be the government. I think where the West kind of excels is the fact that a lot of the governments here are trying to do things that can actually make the city smart because they realize the need for connectivity. Whereas in other countries, this can be a slight issue because if there's no government benefit to them directly, if they don't actually see how that can help them, they're probably not going to back your project. Next is infrastructure. So for a smart city to work in certain countries in Africa, you're going to have to completely change the entire infrastructure. This means road systems are going to have to change, everything from accommodation, everything is going to have to change. Health systems are going to change. And again, the countries have to be really open to that. Next is education of people. So I've actually done some work where I've flown some drones in Africa, in different countries, and people have been a bit surprised that something was going up in the air, and because I go to quite remote villages. So I think there definitely needs to be a kind of influx of education to people to actually make people know what this technology is. You can't talk about smart technology to people who don't know what it is. So you have to basically first put in that education there and then get people intrigued in it. And then last is security and data privacy. I think there has to be some transparency with the usage of our data because everybody knows that smart cities, for them to work, we need to collect a large amount of data and then from that data be able to have some insights. But there's a lot of people who are a bit funny about this and rightly so, because you don't want to be giving your data to a corporation that could use it for whatever the intention they have. So transparency and just having people aware of the data risk is another factor. So I didn't want to go too in-depth because we're going to have a really great lecture from Professor McCann, but I hope this has just opened you up to a few of the issues that can kind of be surrounding smart technology and smart cities in general. Thank you very much for listening. I hope you have a lovely day, and let's get ready for Julie to come up and give her talk.
And Naini, thank you for that wonderful introduction to the talks this evening. My kids left home quite a while ago, and I'm afraid the Marvel films have rather passed me by. So on balance, I was probably pleased and relieved for you moving on to some of those more pragmatic examples, if I can put it that way. Can I remind you all that there will be an opportunity to ask questions of both Naini and Julie after the next talk. But then may I move straight on to introducing the second speaker. Professor McCann's body of practical work unifies decentralized algorithms, protocols, cross-layer dynamical solutions with a particular focus on low-powered, low-resource devices that can act as modern wireless sensor-based systems or future smart dust. She applies this to space, agri and infrastructure engineering challenges encompassing the Internet of Things and cyber-physical systems. Her interests lie in harnessing the various interactions between the cyber and physical to improve security, performance, and resilience. I'm sure, like me, you're very much looking forward to hearing what she's got to tell us this evening. Welcome, Julie McCann.
Well, hello everyone. It's wonderful to be here. This is my first talk since 2 years, frankly. And this is a live audience, which is amazing because I've been lecturing to my screen in my bedroom. So this is brilliant. You're all very welcome, and hello to those at home as well. I'm very honoured to be here to do this talk today. And yes, hopefully I'll explain some of that buzzword bingo you just heard there now. Not all of it's fake, I promise, but some of it is. So you have to guess which is which. So the theme of today is smart cities, and the actual bit that I'll focus in on is the smart bit, okay? And the technologies that I use to try and make that part smart. Now, I'm not talking about AI. That's what we do with the data once we get it. I'm talking about the little computer systems that grab that data for you, that's out scurrying around the city in a drone or embedded in a bridge or whatever, okay? So that's the sort of technology that I'll be talking about even. My name is Julie McCann, by the way, for those who don't know me. I should introduce myself. I'm in the Department of Computing in Imperial College London. Also data-centric engineering person from the Turing Institute, and I'm also Deputy Director of Petrus, which is interested in IoT and security. So that's who I am. Okay, so why would a computer scientist then be interested in cities? Well, cities are very interesting for us because they present to the computer system many challenges. And these challenges are to do with the infrastructure of the city itself, but they're also to do with the fact that there's lots of people in them. And as we saw in the talk just before, more people and more people are moving into the cities. Now, this may be stalled slightly with COVID and so on, but the trajectory was certainly that more people were moving into cities. And at the moment, there's still more people in cities than not. So we're imagining more and more people. Now, this puts stresses on cities. Essentially, the cities themselves are typically bounded by some geographical phenomena, like a river or maybe mountains or whatever. So lots of extra people are coming into this space, therefore it becomes more dense. So there's issues around that, and that presents challenges. How do we manage that? How do we keep people in comfort? How do we share resources into the city, the water, the food, and so on? And then at the same time, we have another set of challenges that are presented to us, which are around the subject area of climate change. So we have, water rising in that large river that typically we have in our cities. And how do we protect people? How do we ensure that the food air miles equivalent is as short as possible. How do we do that? So we look to cities to try and get information about how the city is working, how the people in the city are living, and therefore then we can try to optimize some of those processes. So we take a systems viewpoint on what those processes are, getting food from outside, say, for example, London, into the shops and so on, to see how we can tweak those processes to make them more eco-friendly and make them more comfortable also for the people who live in that city. So this is the point of smart cities, really. So it's to do with convenience, but it's also to do with maximizing the use of the resources, especially when those resources are becoming more scarce. So let's take a walk around the city, and I think I've got my mic slightly, sorry about this. So when we start at home, and more at the moment, we're starting to see our houses becoming smarter. And so I'll just go through my routine in the morning. So in the morning, I have a little machine that wakes me up, and I'll say which one, but I'm sure you'll guess by the tone. It wakes me up and turns on a lowish light, and then turns on the radio. So I've got that system ready to go. And then I tell it to shut up, and then it stops doing what it's usually doing, which is annoying me. And then from there, it's got sensors listening to me, ready for me to tell it to stop. And then it has the lights on and it has the radio on. And then I go upstairs, and right in front of me, my house is upside down, by the way. So upstairs, downstairs is bedrooms, upstairs is living room. And I go upstairs, and I have this panel on the board to tell me that I'm already this week in the red with regards to my electricity. So that's a bit depressing to start me off in the morning, even though I do try. Anyway, but that doesn't stop me going straight to the kettle, and the kettle knows I like tea, and so tea does not boil to 100 degrees, it boils to about 70 odds, and it knows to do that for me. And then the toaster similarly has my particularities about it. If it's very sunny and the sun is beaming into the living room, I can just tell the awning, just say open the awning to 25%, and it'll open the awning for me. And all these things are sitting around my house ready to go. So I've basically got loads of actuators to open the awning, but I have loads of sensors listening for my voice and communicating that. I've also got things like, for example, temperature gauges and so on around the house as well. Then when I leave the house, I say goodbye to the house. It shuts everything off, and it knows to alarm the door, essentially, and I shut the door. So that if anybody comes in at that point, then I get something to my phone to tell me that, yes, someone's come into the house that wasn't supposed to in it, because I've said goodbye to the house. Okay, so you've got this. A lot of people are having these things nowadays. They're off the shelf. Now, when I leave the house, then I walk down the street, and as you can see from the little picture that I've got here, I walk down the street, and underneath me, there's a lot of infrastructure, a lot of utilities. And these utilities are doing the same thing. They're trying to protect the actual resource that they're delivering. And to do that, again, on those, there's lots of sensors. And the sensors are doing things like detecting flow of water, vibration to check that for example, there isn't a leak. Pressure, again, is used to detect that there's no leaks and so on. So we've got a number of these systems out there, making sure, keeping an eye on these infrastructures so that if anything is about to go wrong, maybe we can predict in advance that we need to order a part and so on. And so we can actually get those. And again, back to this notion of making the best use of our resources. We have our smart roads. We've got, for example, maybe we have a scoot system where the system is keeping an eye on the flow of traffic and is also pacing that flow of traffic and allows us to be able to play around with the lights to do so. And in the future, as we're moving towards more driverless cars and embodiments of intelligence in cars gradually, obviously these roads will talk to the car and the car will talk to the road. And between them, we can start to optimize how we can use those roads and make better use of them and indeed make better schedules regarding transport in general. Now, this is a little slide full of information. This is the slide that your teacher told you not to do in a talk. There's too much in it. Anyway, but I wanted to show you the breadth and scope of all the sensor systems that are out in an environment. So maybe if I look, for example, there's air pollution up the top there. You can see that there's air pollution. We have air pollution sensors around London already, looking at to see what our pollution levels are. And sometimes these are used for regulatory purposes as well, so that we can keep track on our usage. And indeed, sometimes we have people who are more interested in building their own air pollution sensors to see if we're tallying with each. If we have a large tree area in our city, then we can have a forest fire detection or general fire detection. We can also have, for example, if we've got an infrastructure where we don't want people wandering into the infrastructure, we could detect whether or not people are there, and therefore give them a warning to say maybe you shouldn't be here, or indeed have people escort people out, maybe indeed. As I said, we have smart roads, smart lighting. Smart lighting can be used to minimize the amount of light pollution that we have, and indeed we could have ways of measuring noise in the city as well. And I think it's just this week they've produced some stats on the impact of health and noise pollution. So we can start to monitor that, and we can do then things like, for example, send to your mobile phone the best walking route that's pollution free and quiet, and so on. So we can start to make nice, comfortable optimizations in the city. So there's loads of things we've got. Waste management, I'll talk a little bit later about waste management, some projects we've been doing. Smart parking, yeah, I've used some smart parking recently, and the car didn't get picked up by the sensors, but that's just a sensor problem, and that's really where I'm going to go in this talk as well. So you can see there's loads, water quality, there's loads of sensors out in the city. Right, so I wanted to show you the kind of system that I'm talking about. Now, the systems I talk about are not big, chunky systems. They're very tiny. This is where I wished I'd gone and got some sort of nail polish on my nails. Anyway, so these are the systems that I'm talking about. You can see it's teeny tiny. On board is a MCU microcontroller. A microcontroller is basically memory and processor and all that sort of thing. We've got lots of sensors. We can have light, humidity, temperature, noise, microphones, whatever. You can have these tiny, tiny wee sensors on them. These are MEMS sensors. That means they're shrunk down to tiny sizes. And usually we have little lights on these. The little lights are there just to debug them, frankly, because they're fairly, let's say, low in resources, and that is that they don't have much processing power individually, these little sensors. So we can't really put debuggers and things like that on them. So we actually have to visually, with our eyes, debug them by playing around with the equivalent of printf for us is turn on the sensor light, okay? So that's how we debug these, so that's always fun. Anyway, and that's pretty much the size. We can shrink these down to tiny sizes, which you'll see later on as the talk progresses. So this is sort of what we're playing with. Now, the deal is with these, and this is what my particular area of research is, to keep it at this level of resources. The level of resources I would describe as being a bit like, the games machines in the 80s, your home computer in the 80s. That's what we're talking about. Tiny, tiny amounts of processing power, not much more. And the nice thing about that means that we can use either batteries to power them, or indeed harvesting to power them as well, which means we can then start to do the retrofit that we were talking about earlier, okay? So you can start to do that retrofit. You can put it in places that you don't have to run cables to. And they're typically also have transceivers on them, and the transceiver then allows us to use radio for communications. And so we've got our processor, we've got our sensor, and our sensors, indeed, and we've got our means of communication. So that's the three main components in these tiny little systems. Okay, so these are the things. Now, within that spectrum of technology, this is the juicy pieces of research that I get into, right? So these are our boundaries of research. I don't have a supercomputer. These are my boundaries. So essentially, our city IT challenges are a number of aspects that we have to take into account. When you're building something into the city, one of the things that dictates how we build it and the type of computer system we build is to do with cost. Now, we consider those systems to be frugal in terms of their low cost, because you can retrofit them, therefore you can set them out. But also, the actual units themselves can be a few pounds, okay? They're actually cheaper to produce, but if you do a big run, you can get them down to a small cost. And so what we do is we can either use a low-cost sensing to bring that down, or we can use participatory sensing, and I'll talk about that in a second. The other challenge that we have to bear in mind is scale. Scale is in terms of the numbers of devices in a given space. So all those devices are physically there. They'll be trying to communicate maybe at the same time. The air can't hold the communications all at the same time. Therefore, we have to think of better ways, better protocols to make it such that all the devices get a fair chance to be able to communicate their information. We have to bear in mind how these devices are intercommunicating with each other, and so we have challenges around that. And as I said before, the air only holds so much communications at a moment, so we have to look at network capacity, which everybody who works in networks has to do. But if we're talking 10,000 sensors in a small hand device, then we're talking about serious network capacity challenges. And then, of course, the obvious one, if these are out looking around their environment, sensing their environment, we want to be able to trust that the data that's coming in from these sensors is worthwhile and accurate as possible. Now, in truth, we don't trust a lot of them. We have bounds of errors, and we work with those bounds of errors. The system itself obviously can't be sensing personal data when it is supposed to be, so there's that side of trust as well. And then because we have low expectations, let's say, for these kinds of systems, these low expectations means that we build them in a way that they're agile. So we're kind of expecting failure to happen, so we embed that knowledge inside the system itself. So let's start off with that. So the typical things that go wrong with these kinds of systems is that they're noisy, they're prone to decalibration. That's the actual sensor itself is now misreading in some way. They can be misplaced, or indeed, we have had sensors taken and moved by people with hoovers. Or, in fact, there was a storm about 4 years ago. We had sensors in the Queen Elizabeth Park, and after the storm, one of the sensors that we had, we noticed on our chart wasn't relaying data anymore, and it was because it was put through a chipper with the tree that it was attached to. So they can be moved, compromised, indeed, through a chipper, and degraded. That's very much degraded, I think. So the deal is that we look at them at two levels. We look at them at the actual sensor device. I call it sensor-based system. The sensor-based system device level, trying to get all the software, the sensor working properly, the communications working properly, playing around with energy and so on. We look at that. But the real juicy, interesting bit is in the network of these sensors, and that's where the intelligence is. And this is why I've got this little picture here. If you see these little pictures here. What's interesting about the way we program these systems is that we don't have an operating system on a lot of these computers, even. They're just what's called little runtimes that schedule at the most 2 threads. If anybody programs, that's all they're doing, really. They're pretty dumb, right? So what we have to have is embedded in next to no lines of code, some form of intelligence that they will root round failure, that they will keep themselves alive as long as possible, that they'll actually do their job, which is to sense and send your data back to some server somewhere. So the way we've approached this is not unlike how it happens in nature, as it turns out, okay? So I would say it's not nature inspired, but it's kind of parallel to nature. So for example, if you take a firefly basically to mate, it wants to flash its tail at the same periodicity as the other fireflies. And so what it does is when a firefly joins the network of other fireflies, it knows what its flash periodicity is, and then it's looking at, I do it as a dance, but it's looking at all the other fireflies to see what theirs is, and it looks at the one nearest it and it thinks, if I sync with this, I'll sync my flashing with this, then it starts to flash with me, its neighbor starts to flash, and then this gets permeated across the whole firefly network, swarm, whatever you want to call it. And so they're all then doing the same thing. So they're all have made little adjustments to their neighbor. We do exactly the same, and I'll show you exactly what that is in a second. So, for example, this is a field full of sensors. It could be let's say, a vineyard, okay? It's a vineyard full of sensors. I have one sensor that needs to send its data back to the base station, which is the base station looking thing. And what it wants to do, it wants to get its data back there so it can go off to some lovely server and do some analysis so that you can predict what your, yield is going to be this year, so you can buy your bottles so that you know early enough what you should predict. So the most obvious way to do that is to take the data off the sensor and send it to the base station, okay? But there's problems with that. And the main problem with that is, for me to be able to send that data across that field would require that I send it at a decent power so that the radio signal can get over to the other side. So that means I have to put more power into it, which is kind of not what we're about in the low-powered kind of computing end of things. So there's alternatives. So the alternative is to reduce the range of the communications and instead do this thing called multi-hopping. Sorry, I was going to just say, yeah, the other downside is that you can't go through mountains or skyscrapers as well. So that's another problem with sending a single signal across. So what we do instead is we reduce the power on the device only to be what the distance is there. And instead we multi-hop that round, okay? So we're multi-hopping that. And the nice thing about that is that it can route itself around obstacles. And obstacles could be something like that mountain where what you can see, but it could be an obstacle like a very powerful piece of other radio equipment that you can't see, and you're just not getting the signal through, okay? And indeed, one of the vineyard examples that we did in the past was in the vineyard itself. It had a slight dip in the where the grapes were. You couldn't see it with your eye, but radio wouldn't go through, and there was nothing there to block it. It was just one of those weird things. Turned out the grapes behaved unusual in that spot as well, so there you go. Anyway, so the alternative is to, as I say, and then the second thing is to when you're routing and you find that one of your nodes has died, because we're agile in these kinds of systems, we expect our systems to die because they do. So we have to build in some way of routing around that. And so again, it's this notion of multi-hopping. Now, how do we implement that in a very low cost way? And I mean cost in terms of code and in terms of what you have to store, okay? So we can't store the route from the little sensor all the way. Now, when I say store the route, that is knowing I have to go from A to B to C to D, E, F. You know, we can't do that because that takes up, you know, it could be 10,000 sensors. If it's 10,000 sensors, I can't store that on those little computers that you saw earlier. I haven't got that space. Furthermore, we know because some of the sensors die, a bus could drive in front of a sensor and it can't talk to the other sensor. Therefore, we need the agility. How do we get that agility in? So we do something really simple. And this is one example. This is collection tree protocol. This isn't one of mine, but I've built something similar. But I thought this is easier to illustrate. It's about 14 years old. And it's very simple. What it is each node, each device, only knows its one hop neighbor. That is, the equivalent in this room for me now would be that person, that person, that person, and maybe you two, right? So you're my one hop neighbor, maybe you two as well. And you're my one hop neighbor. I don't need to know how my message is getting across the auditorium, okay? And so I just know who you are, the one hop neighbors. And from that then, what I do is I talk to you to say, hi, you're still alive, great, I know you're still alive. You're one of my candidate starting routes for me to send my message. Now, when I'm talking to you, first I want to know you're alive to take my message, and two, I want to know how good you are, okay? Because I want to improve the route. I want to get it across to where it needs to go, either as fast as possible or more reliable as possible, and so on. Now, in CDP, what they have is this thing called ETX. And ETX is a tiny little thing. You see there, the ETX is that little bit there. You see that little bit there? Very simple calculation. Basically, I'm wanting to know who of my candidate first hop neighbors is the best. And best in this case is the one that's the most reliable. So what I do is I send a little message to each of them, well, actually a few messages, and check how many of them have disappeared. And if one of them say, you're going to be my one hop neighbor that disappears. If you keep dropping my messages, you're not good enough, sorry, not right now, but you might be good in a minute, right? And so I'll pick up the one that is really good, the one that has the best ETX value. And that then means that that person then, when I sent my data to that one, then they do the same, they've done with their one hop neighbors, and then that then ripples out across the network. And that tiny wee calculation is all I need to do that, okay? Hopefully you get that. So that tiny calculation. So I'm basically looking at how many packets you drop when I send you a message and how many packets are dropped on the way back. And I pick the best of all of those, okay? And the aim is to have a lower ETX value. So it's basically literally a gradient. Imagine it going down a hill. You want it to run like water down a hill, the message essentially. So you could use this, but you can make it more sophisticated. And nice things about these kinds of techniques is that we can play around with understanding their behavior. We can see if they're optimal or not and what the bounds of optimality are. And so we look into that. We also look into adding other things. So for example, I might go for reliability, which is the vanilla ETX. I could add on maybe say, for example, if these people here had better energy, then they're going to last longer. So maybe I'd lock into them more and so on. So I can add to it. I can add, the weighting of how much battery power they've got left and so on. And so that basically is how a lot of our protocols work. It's that very simple. I have a relationship with my one-hop neighbors, and then they have the relationship with their neighbors, and then the intelligence, let's say, ripples out. So unlike insects and so on, our systems, unless they're attached to a drone, don't scurry around looking food. So one of our Achilles heels in these kinds of systems is the fact that we have to power them up. And a lot of the time, the work that we look at is how we can, in a very frugal way, get energy to them. We can have batteries, or we can have harvesting. And we have to do some sort of way of deciding when the system decides to sample, i.e. sense, when it decides to process and how much it will process, and when it decides to send. And there's lots of factors in that. So we have to optimize all those factors and optimize them together so that the node itself, the device, the little computer, doesn't run out of energy in its own right. So we look into that. We look at, for example, how much energy we've currently got, what we think our energy is going to be like in the next epoch, the next window of time. And then we do some sort of budget allocation as to what then we should do now. How much sensing I do, how much processing, and how much sending. And obviously, sensing costs a good bit, but not as much as sending the data. The radio is very expensive. So we've looked at that, and we've also looked at ways of making the actual battery itself, the rechargeable battery, last longer as well. And one of the things that we found is that we could double the length of the lifetime of those batteries by scheduling our code differently. And so that was quite interesting. And now we're looking at the next generation, which is to take ambient energy. So the Wi-Fi signal in here will allow me to power up my little device. So we're looking at that now as well. So that's the next thing. And we're building new protocols to listen for radio, power up the radio, or power up the device, send data when we've got enough power, and so on. So we've got a new cycle of what we have to do, and we have to optimize over all of that. Now, you see, across this, there's a little set of stars that I will have throughout the talk, and it's this thing, cyber-physical interaction, so you can get your bingo books out now. So cyber-physical interaction is where I'm having to understand the behaviors, like Turing, understand the behaviors of my computer system from a cyber perspective. That is the code that's running on the machine, all the different tasks it has to do, and so on. But I also need to know the physicality of the environment that computer system is in to be able to understand how I can make the next decision. In this particular example, it was how much energy opportunity is coming next. What is my prediction in energy opportunity, and so on. And so you'll see these little stars throughout the talk, and I'll return to that as I go along. Now, one of the other things that we have as a challenge is how we can get lots of these systems communicating around the same time. So when they want to sense that they can send, and the only impediment is their own ability to do it at that time, not the fact that everybody else is communicating. Now, we have lots of challenges. We're in the low-powered end of things, right? So we're easily jammed, obviously. We're easily interfered with, let's say. And also, we've got lots of our system, and then we've got lots of other systems, and we've got microwaves and all sorts of things that interfere with us. So we have to think of protocols and nice ways of doing that. Now, more recently, people have moved away from that multi-hop, jump and jump, jump nature of building these kinds of systems because they're awfully hard to maintain. Though it's so very simple to write a program for and play around on simulators, sticking them out in a real environment has become very difficult. But that's okay, because we've got new systems now, new protocols that make better use of the low-powered equipment, essentially. One example is LoRa. Those of you who have used it, LoRa basically is a low-powered wide area networking infrastructure. Essentially what happens is you have different ways that you can send your data, and you can sacrifice how long it takes to send the data to get good distances. And theoretically, you can get distances up to 20 kilometers. In a city like London, we've been getting 8 kilometers max on these kinds of systems. So that is, using the same low poweredness that I described before, we're getting kilometers worth of distance. So this is really interesting to us. Now, there's still, of course, lots of challenges in those. And one of them is, again, back to we're in a city. We've got lots of people wanting to communicate at the same time. Therefore, we have to share that better. But what if we looked at it in a different way? What if we thought, right, okay, interference we consider bad. What about if interference is not so bad? What if we try and look into that? And so what we're doing here is we're taking what we normally do, which is to divide up when we send and sense and so on, and how we do that. Instead, we just let it all happen on top of each other. So you can see this is the way we would normally sense. You've got like the first piece of message here, second, third, fourth. Instead, what we do is we let them send. We're a bit creative about how we let them send, but we play around with that. And what we do is then we've got all these signals coming into our receiver. And then what we do is we take that messy old signal and see what we can get out of it. So the first thing we get out of it is the strongest signal first. So the big, powerful signal that we can get. We can use signal processing filters and so on to grab that signal. That's it. We've got it. Good. Right, that's to the side. Then we go back into the mess that remains. And from that, then we get our next best signal. And that's the yellow signal in this, or the green signal in this one. And then subtract that out again. So we've got our different signals as we go along. And when we go down, basically, the powers until we cannot determine what that signal is again. Which means then lots of communications can literally happen on top of each other at the same time. And so we play around with that. We play around with how we should set up the powers, how we should set up the receivers, and we try to optimize that. Now, it's very expensive to place base stations and sensors and so on out in a city. So we also toyed with, what if we could just borrow infrastructure that's already there? One example of that would be a piece of work that we did in the Queen Elizabeth Park. And this is where we were looking at building what's called an opportunistic network. So what we've got here is our sensors are out in the park. Looking, I don't know, our sensors were looking at the environment to check the environment was okay, the temperature, the trees were growing properly, that sort of thing. Anyway, they're there. Then we've got numbers of different people walking around the park, okay? So they're walking around the park. I'll stand over here. And you can see that this person has walked by one of our sensors, okay? So it sends its little message to that person's phone. Now, meanwhile, that person has been very kind to upload our little app that sits in the background of their phone. It keeps everything private, and it doesn't use up their battery, and it doesn't impede on any of their other apps. It's just sitting there waiting for the sensor signal to send its little message. When it does that, then this little person walks along, meets other people across the way, and the message then jumps to them, and then jumps and jumps until it gets back to Imperial, essentially. Now, the interesting thing is that what we did in that was not unlike the objective function or the little, the gradient that I talked about in CTP. It was very similar. But what we added was the following. Firstly, is the message able to talk to that person in a clear way? So it's the same PRR, the same way we did it in CTP. In other words, is the signal reliable? The second thing was, it has that person's battery in their phone. What level is it at? And we check that so that we can make sure that when we send the message, the phone's not going to die midway through the relay. And then we also looked at, we kept an eye on how popular the individual was in terms of who they meet in the city of a given day, right? Because if we relay through a more popular person, they're more likely to meet other people, and therefore our signal's more likely to jump across to all the different people. And we ran this in the park. We proved that it would do the job, that it would get the data, ship the data around in a nice way, that it was optimal in terms of doing that. Where there was a chance of relay, it did do it properly, and it did it in an optimal, fast, reliable, blah, blah, blah way. But we also did, why would somebody want on Earth to put an app on their phone for my sensor data? So we put a little token system in whereby you were rewarded every time you sent data. And so we used, interestingly, some of the mathematics from the finance world, things like mechanism design and so on, to make sure that people were guaranteed that they would get their tokens proportional to the amount of work they've done, and also to disincentivize them for cheating. So we did that sort of thing too. So we got to play around with that because we were lucky because we were on mobile phones and we could do more expensive things. And again, there's cyber-physical interaction there as well, because we're looking at the physical world around us. We're looking at the humans and their centrality or their popularity and things like that. Another thing we did was looking at how we could share infrastructure. So if you've put a sensor network out and maybe a water network wants to go out, a water network sensor wants to go out, and maybe, I don't know, the bin chute system wants to go out, could you share it? And we looked at how we could program that. And so what we did was we looked at how you would abstract away all the details of programming and see what it was like to program a city. And we looked at that and we did some tests on real programmers, people who are more hacker sorts that don't program day in, day out, and some non-programmers as well, to see if they could program the city. And that was reasonably instructive for us as well. So that was fun. We also looked at how you would use a control system and how you would make guarantees about how long it takes to send a message, because that's needed when you've got actuation. So if you're trying to switch a pipe between A and B, you need to have you need to know when that's going to happen. So we started playing with that as well. And we showed that if you do a lot of onboard processing of the actual sensor data before you send it, that you could get better guarantees of being able to build essentially a wide area control system. And again, that's the cyber-physical interaction things. So what's the sort of things we do? Well, the sorts of things that we do is we look at, for example, water leak detection, or indeed, which is actually more important now, which is water leak localization. So we could use triangulation to actually pinpoint where the leaks are. And we were lucky, we got that down to plus or minus 50 centimeters. So that was pretty decent. In Singapore, the aforementioned Singapore, we have a sort of sub-lab in Singapore at the minute, and we're doing lots of different things, one of which is in Singapore, the large housing systems there, the bin chutes, you basically throw your rubbish down the bin, and then it's sucked away. Rather than have all these lorries drive up to the bottom of your tower block, the rubbish is sucked away along these chutes, these pipes. And so obviously they get dirty, they start to deteriorate. And so we send a little, what's called a pig, down to analyze the pipes and to determine whether or not some of the pitting in the pipe could cause a problem in the near future. So we do a lot of that work. We do a lot of work on how to recycle water. So this is water coming in from rain on top of the large buildings. And again, what we're looking at here is how we can, when to decide to keep the water on the roof, when to flush it when a massive storm's going to come. And to do that, we have to do near casting machine learning to be able to know when that storm is going to come and get an estimate of how how much water is going to come as well. And so we mix our normal weather sensors there. We use the solar panels as a sensor. And we also have little cameras to determine the kind of clouds that we've got, because this is actually quite hard to forecast. And then that water then can be flushed down to either, unfortunately, into the sewer system or into a blue-green container that maybe is under a football pitch and it's feeding the grass and that sort of thing. So we've got this control loop and we're modelling that with some of the other members of Imperial College as well in chemical engineering. And we've also looked at the security of these systems as well. Now, the very agility that I mentioned earlier is actually a negative in the sense that it causes the system to be easily distracted and easily led astray, let's say. So what we've been doing is we've been looking at all the different components within our system, all the different layers, and identifying where the problems might be. But what we did is we looked to see what is the negative to see if we could get the positive. One of the things we looked at is that we can't really do heavy processing because the processor can't cope. So what we did is we looked at how we could use the sensors and indeed the radio, the transceiver itself, to produce a key to allow us to build better security. So we did key generation through our sensors. So that in a way, it's a physical systems computation instead of us doing maths over the processor. So we did that. And then another thing, back to this idea of looking into what is usually considered the noise, the rubbish. Let's look into how we could use that. So this is basically a project called, well, it's nicknamed Cognisense. It's also called RF TACO. What it does is it sends a radio signal through a rotating machine, and then the disturbance at the rotating machine, that normally when we're doing communications, we wipe out. We're not interested in that. That's a disturbance. But because we are detecting it, we're now interested in it. So if I'm sending a normal radio signal, it could be Wi-Fi, it could be anything, Bluetooth type signal, out, and I'm listening back to hear the disturbance in it, I take that signal out, and that is the rotation of my machine. And I can also get the vibration of that machine. And we've taken that now a little bit further, and we're using it in the vineyard. So we've got it basically now determining the amount of water in grape bunches, and we're also using it to understand what bugs are out there in the environment as well. So we can use that. So we have no sense. The sensor is the same transceiver that you use to do communications. So we're trying to reduce down the complexity of these systems. So I've been hinting about the cyber-physical interaction, and I wanted to give an example to make it more concrete before I finish. So cyber-physical interaction, the example that I've got here is a water network. And in the water network, I'll just use the pointer again. In the water network is the gray part there, okay? In the gray part. And then we've got these little sensor nodes. That's the yellow, if you can see those. And we've got all sorts of base stations and so on. Now, here's the thing. The water network is designed to deliver water to you on demand to your customer demands, right? It also has to live long and keep its costs down and not break and all those things. So when you're optimizing that, that's the sort of things you take into account. As a computer scientist, I build the computer network. The computer network needs to live as long as the water network. London's water network is 150 years. I don't know any computer sensor system has been that long. It's been working that long ever. So, but that's the aim. So I have to keep it so that it lasts as long as the physical infrastructure that it's monitoring. I have to make sure that it is optimal in its own right. Its messages are getting through as fast and as reliably as possible and so on. We thought we had this brilliant idea. We'll try and get the lifetime of our devices as long as possible by placing them on the actual physical pipes, and we'd use the vibration of those pipes to power our little systems. And here it's brilliant because we are actually we're in control of the valves, the actual things that route the water around the network. Therefore, we can decide how much vibration we're getting on the pipes. Isn't this great? We can keep those systems alive forever and ever and ever, right? Except when we were starting to play around with the vibration to get the power for our little sensor system, it was causing transients, waves in the water pipe, which then limits the lifetime of that water pipe because it's smacking in terms of pressure later on. Now, here's the thing. Here's what I'm talking about cyber-physical interaction and why it's important. It's important because I designed my computer system and optimized it perfect for it. The water civil engineers, fantastic. They optimized that pipe network as best they could as well. But we didn't match up. We were actually at odds with each other. And we keep seeing this so often. When we describe the computer system, we have a digital twin of our physical system. But our computer system is also a physical system and is bound by the physical world. It has, temperature changes its way of processing. Its sensors can be played around with if I put some ultrasonic sound near it. Those kinds of things happen. But we don't build a digital twin of our computer system, and we rarely integrate the two. So this is the thing. This is what I want to look at. This is exactly that. How do you build these types of different systems, a digital system, very discrete, a continuous system, the physical system, and the physicality of the computer system all into this mess? How do I model that? It's not easy, but I have no answers yet. But we're working on it, so that's what we're doing. And so to the future, one of the things that was mentioned was smart dust. But before that, some of the other things that we're looking at is, for example, being able to print the sensors in situ. The robot bridge there is a piece of work that we were working with in Turing, that out in Amsterdam, the robot built the infrastructure for the bridge. But we're now talking about ways we could physically get the robot to also build a sensor by printing the sensor as it's printing the bridge infrastructure too. And some of the work that we're, to that end, working on is how we could build a CubeSat that is basically a 3D printer, and it's printing the sensor in space. And this means that if we go out to space, we print our sensors, we discover something new about space, we can then build new sensors to better understand whatever that phenomenon was. So you don't have to send out another CubeSat, which is really expensive. So we can do in situ changing of our missions. So that's the sort of future thing we're looking at as well. And then we're also, there's a sort of Friday afternoon playing around with is, what if we shrunk everything down to dust size and asked it to form a pyramid and become a, I don't know, Wi-Fi router or something like that? Wouldn't that be fun to be able to say, could we program something like that? What would the technology look like? How would it physically bond together to form the pyramid? And so on. And so we're looking into some of that. And as you see, now we're into the realms of sci-fi, where you can imagine smart matter. And before I finish up, you know, there's a lot of challenges I've mentioned there. Some of these systems are flaky. People are worried about them spying on us and so on. But wouldn't it be nice if we could work it all out and iron out all those problems? This is a poem from back in the late 60s, and hopefully it gives a nice positive end to the talk.
In 1967, a young writer called Richard Brautigan crystallized this. One morning, he walked through the streets of San Francisco, handing out a manifesto. It described a future world held in a balanced equilibrium by the fusion of nature and computers. It was called All Watched Over by Machines of Loving Grace.
I like to think, and the sooner the better, of a cybernetic meadow where mammals and computers live together in mutually programming harmony like pure water touching clear sky. I like to think, right now please, of a cybernetic forest filled with pines and electronics where deer stroll peacefully past computers as if they were flowers with spinning blossoms. I like to think, it has to be, of a cybernetic ecology where we are free of our labors and joined back to nature, returned to our mammal brothers and sisters, and all watched over by machines of loving grace.
Machines of loving grace. Thank you. Thank you very much.
Julie, thank you very much. Not only do I have very low exposure to Marvel films, I live in a house with the bedrooms upstairs and a clock radio in it. So I'm feeling a bit technologically challenged, but I'm sure there are others in the audience who are at much more advanced levels of sophistication. Can I ask Anani to come back onto the stage for us, please? And we have the opportunity now for some questions. Can I remind those of you watching online, please do put your questions in the chat and participate. Is Calla somewhere? Oh, you're over there. I was sure you're going to be over here. So Calla's monitoring those questions. I believe we also have two roving mics. I can see one there and one there. So if you would like to ask a question, please do indicate that in the normal way. And then could you wait for the microphone to come to you, state your name and affiliation, and ask your question. So who would like to start off with? The gentleman at the front here caught my eye first. The mic's just coming from one side to this side.
Hi there, Peter Gribble, Intelligent Mobility Consultant at Arup. I'm very interested by what you were saying about the cybersecurity stuff. I think it's going to be a really difficult challenge, particularly when you're talking about low power, quite simple devices that could be 50 years old by the time we get there, connected to all these new pieces. You want connectivity between all your devices so it's more efficient. And maybe they're owned by different people, and some of them are safety critical, and some of them are owned by people who care less about cybersecurity than you do. So I guess the question is, what do you do about that? How do you find a way to get those benefits without leaving yourself vulnerable?
Yeah, well, there's no straight answer to that at all, as you can imagine. That's a very complex system. So the legacy systems that we have to understand we have to better understand what could go wrong with them. If we can articulate that and model what the impacts of that would be, we could start to mitigate some of those problems. Integration between these different systems is very complex. So again, this is back to what I was talking about earlier. We need better systems ways of modeling the system so that we can understand the impact and those interfaces and those impacts as well. There's a lot of work at the moment looking at how we can make these systems more reliable from a security perspective. And obviously, a notion of upgrade towards that is important and how we do that. But we don't have, if you look at a data center, you've got lovely ways of first articulating the performance and the safety and the security and how to software and hardware engineer that so that you can do updates and so on. We're not really there with these yet, and that needs to be done. So I have no answer to you.
Thank you.
Thank you. Yes, gentleman right next to the other mic.
In City University. Hi. Yeah, the same problems of feedback and cybernetics, second and third order cybernetics, occur at the next level up when you're into the social society as well, where the desires and the lacks of the user community are influencing the way that demands are placed on the system from the user end, not only demands being placed on it from the supply end. Yeah. So you really need to integrate your system all the way up, not just from bottom. As you're seeing gradually, you're seeing this happening at the medium levels. It's going to happen more and more at the upper levels as well, especially if you're talking about big socioeconomic systems like cities.
Exactly, yes. Yeah, and also these kinds of systems were maybe designed to be used one way, and as they go out there, exactly, they can be used a different way. And I remember you telling me years ago, probably about 25 years ago, about feature interaction and how a system was designed for one thing. It's a bit like what I was talking about in the water, and then you are using it for a different thing, and the two interactions clash with each other and cause a security problem.
Well, we've gone beyond feature interaction in the last few years. I've now got a way of modeling systems in exactly the way you want to do it, I think. So we should talk about that.
Absolutely. Thank you.
I wonder if I might use host privilege to build on that question in a slightly tangential sort of way. And one of the things that struck me about the two talks was kind of potentially the difference in the applications between your examples, Julie, and some of the things that we're hearing about in Africa and developing cities. And I wonder if you could each say something about how you felt some of this technology might start to migrate, can I put it that way, from some of the more, I may not be right, but the sort of more sophisticated, developed world type applications into the global south and those sort of contexts. Do you have any thoughts about that question?
I think from an African perspective, there's so many different ways that we could use these, like especially the systems that you were talking about. I mean, things from monitoring like the energy usage and just trying to make sure that we're not using too much, and I would again go back to the systems that you were talking about, because you could use it today to do A, tomorrow to do B. But in your question, what context, were you talking about in developing countries?
Well, interesting question. I mean, I was particularly interested in your transport example, actually, because that's an area that I'm quite familiar with. So
like the different applications?
Yeah.
Yeah, I mean, again, you could use it for logistics, so delivering items, and you can use it for healthcare, you can use it for different things. But I think the way the technology is going anyway, there's so many different applications. So
yeah. I mean, if your question is about how you take something designed for, say, London and bring it out to somewhere else, maybe it's not too much of a difference, to be honest. The downside of having to design something for the likes of London is that everything has to be retrofitted, and you've got all the other mess that's there. If a city's being developed maybe more from scratch, like some of those ones you were describing, you might have a few luxuries there where you can co-design with the designers.
City
and that to me is luxury, to be able to do that, to be able to place the sensors in their ideal spot rather than have to work out what on earth is a half-decent spot, like in London. So, and I mean, these are cheap. These are not expensive. And there's, you know, if you're paying big money for them, then it's just because somebody's charging it as a business model. They're dead easy to make. And so there's no, well, there's a slight impediment. The biggest impediment is being able to place them somewhere and maintain them. That's the big costs, really, that I see. The actual devices are cheap.
Okay, thank you. A question online, maybe.
I can hear you.
He is asking, how do we weigh up the benefits of technology in a smart city against the need to reduce our use of fossil fuels to generate power? Does investment need to first happen in infrastructure and renewables?
Yeah, I definitely say that. I mean, again, going back to the technology and the different applications, it's not so much the technology itself, it's more so the people around it. So I think before we can talk about smart technology, we have to talk about smart people and smart governments and smart people coming together, because it's mostly the policies around that.
Yeah, I agree, actually. I'm trying to think of what to add, actually. The systems, yeah, I think that these little systems in terms of the power that they consume is so tiny, yeah? But there are, I mean, they are made of plasticky stuff, right? And resources. And I do have, in a field somewhere in the UK, a bunch of sensors rotting still to this day because they've been decommissioned, but they've never been taken out. So that's not good. And because they don't last very long right now, that's happening. The other thing is the data that they supply is plentiful, and it's going into these big servers, and you're wearing away all your machine learning and whatever, and that's consuming countries' worth of energy. So we have to get that right, because that's, in terms of the amount of resource being used there, that's airplane levels, and these are your watch levels. But the actual better ways of looking at biodegradable systems, maybe, that sort of thing is required, I think.
Thank you. Maybe a second question while we're with you from...
Sure. Another one is from a whole Team Electrical E5 Group. Would it not be smart and agile to just consume less, make less, and have smart management solution written down rather than relying on huge amounts of energy? Will it make us lazier?
I mean, I wish we could say that people should just use less of this or use less of that, but it's never that simple, is it? So I don't know. Do you have anything to add to that?
It has to be combinations of all sorts of everything. But how many people are going to go without water? Mm. You can't. So we have to make the best use of what we've got there. And if a little bit of cost in terms of technology and energy to do so, surely that's worth it. So that we can look to the things that we can reduce and catch a grip on, but there's other things we can't. There's no choice.
I'll comment briefly as well, if I may. I was interested in your water example, Julie, because I've been involved in forecasting in the water industry for quite a while. I mean, I don't know how it is these days, but time was, when you're talking about leaks in pipes, I mean, the amount of resources that are being wasted in these systems is really quite phenomenal. I mean, we're talking about 15, 20, 25% back in the back in the day. So I mean, I think you have to think about sustainability from that kind of point of view as well. It, to some degree, it's a basic, sort of cost-benefit type calculation about what you're saving as opposed to what you're investing. It's a slightly different question, but related, I think. Another hand in the room, gentleman in the centre here.
Hi, my name is Paul from PQ'd. Do you think that with the smart cities that you're talking about, particularly in Africa and the Middle East, that we'll see a shift in the geopolitical landscape and that people will stay there, or are they going to become sandcastles that people just leave behind because things like the water and everything else, it sees a migratory move northwards?
It depends. I mean, There are some smart cities that have turned to sandcastles, and I've seen the pictures, so it's interesting that you describe them that way. I think if the delivery of utilities and so on are so difficult into those areas, and the cost per individuals, then they're going to move somewhere where it's cheaper, of course. But if people need to live there for some reason, I don't know, to do with work or something, then maybe we can try to make it a little bit more comfortable for them through using these technologies to make sure that those utilities are fine. But I would say it depends on, people need to work and they need the utilities to be able to do, to live when they're not working, that sort of thing. So I think that's where it's based on. It's very old-fashioned and nothing to do with tech, really.
Okay. I'm not sure if I saw a question up there or a... Oh, yes. Just to the right of you there.
Good evening. Paul Campy from RICO Europe. We've already seen examples of crowdsourcing data from individuals, particularly for smart transport solutions. What do you think the role will be of people as the sensors, of using people's devices, people's wearables, rather than the sort of sensors, the hardware sensors you're putting in the field, for example, in the Elizabeth Park, over and above using it as a communication mechanism, as you described, sort of a mesh network?
Yeah, no, we've actually been working on that sort of thing. So that's basically where you have either people through their sensors on their phone, for example, relay information about temperature and whatever. They obviously join the network and we give them whatever incentivization to do that, or they're just doing it because they're nice. So that you have that. You can also let people scurry around and find information for you. So that's another one. And for those of you who love optimization and financial mathematics, we use a lot of those for that as well, to make sure that we have guarantees that the data coming in is truthful, it hasn't been adjusted in any way. If they're going out to find the information for us, like is it congested up there or something like that, that they're not going to lie. So we have incentivization mechanisms that we use to try and encourage the truthful data, and to try also to, for example, give out workloads so that if we give out a workload to say a bunch of people over there, and these bunch of people are close enough to be getting a workload similar, to check that the data is pretty much close. Therefore, we can say the data has a certain level of validity. So yeah, there's loads that can be done in that.
Yeah, just to add to that, I think there's certain contexts as well where people are actually happy to do this. So there's an app in the UK called Fix My Street, where people can literally see a pothole, for example, and report that to the government. So there are cases where people naturally would just want to give up that data, and the chances of it being quite accurate are quite high because you're taking pictures, you're sharing it. So yeah, I think situations like with Fix My Street, you don't really have that issue too much.
Yes.
Good evening. Mine's more of a three-part question. My name's Madhav, me, myself, and I. So we're talking about electronics and smart cities, but it would be amiss to not discuss the fundamental resource problem we have. For example, you mentioned vibranium. Now, coltan is the equivalent of vibranium, and it's mined in the Congo. It's mined by child miners. A lot of it finds its way in unallocated fashions in supply chains through to China, and then goes into all of the electronics that we use. So that's a massive problem. How would we resolve that issue? Secondly, that leads on to EVs, and that sort of issue of coltan expands to, the platinum group metals and also the alkali earth metals. If Western cities wish to transition to electric vehicles, it's sort of fundamentally not viable with the current technology that exists, and that sort of leads to battery technology. So how do we propose, or how do you propose we sort of get around that problem? And then sort of there's this scarcity issue of energy. Now, the sun is the most abundant energy source on the planet, and solar cells are made from sand and silicon, which is fundamentally infinite. So really we're constrained by sort of rare earth metals, platinum group metals, alkali earth metals, and things like coltan and cobalt and so on. So it's questions of supply chains, where things are refined, how things are made, and and how those resources are distributed around the world and who benefits from those resources. And so how would we make a world where the people that are mining the resources get to benefit from the wealth generated by those resources, which feeds into a more equitable way around the globe, ultimately?
Hey. Just kind of a summary to all your questions, although I will have you please repeat the first one. But as a general summary to all of them, I think it goes back to the government. I think, for example, in Ukraine, what they've done is that a lot of public companies and even private companies have to actually share their data. They've made an open data system where you have to share your company earnings. That transparency has to be there because they're trying to fight corruption. And I think in this context, it's, it has to start from a governmental level. There's not much us as people or even the engineers or the people creating the technology can do. And I definitely say it just goes back to governments and the progressiveness and them trying to be willing to actually sort out those issues. Like you said, the children who are mining, things like that, it's an institutional issue.
And also, one way that we can use these kinds of systems is to check on it. So if somebody's regulatory rules are not to use children and source some, in this case, metals or food or whatever, we can get the provenance of it. We can use these kinds of systems to track throughout the processes where everything came from, assuming it's secure and hasn't been played around with. Let's assume those things. Then you can see where everything was coming from. And then you can say on your whatever widget, none of the components of this comes from, naughty people. It comes from the more respected or whatever. It's not going to change the fundamentals of taking the stuff off the earth. But if the governments do get together and then people purchase their components from the reputable side, we can track the provenance of those, and that works with food as well. So one of the things I'm looking at the moment is logistics generally and designing tiny lightweight tags so that they can be not destroyed in any way, and trying to get them so that you can understand from what mine things came from or what form things came from and where they've been in between.
Potentially going to upset the gentleman with the microphone now, because I think it's always good to ask people who ask hard questions whether they have any. Was there anything else that you'd like to say in terms of an answer to your own question? If not, it's fine. But go on, yeah, just briefly.
Yes, mine's were more. It was more of a statement rather than questions. But it was, we have to get around the problem of resources. The people that have the bottleneck on this are OPEC, and the oil cartel. It's not a secret. They've been shelving lots of renewable tech for generations, and until we address that problem, it'd be a miss to talk about all of the world-saving energy issues. Energy is not scarce. It's how do we harness the energy that's available in a free way, and as Tesla would put it, free energy, and that's the problem. And ultimately rewarding the people that are mining the resources. So why not take refining plants to Africa, for example, rather than shipping all of the resources from Africa to Asia, then producing the electronics in Asia, and then shipping the electronics from Asia to America, and then to the UK or to Europe, for example. And it's the supply chains, as you touched on it, mentioned, that is the fundamental problem. Yeah, I could talk about this, and I don't want to take up more time because I'm sure other people have questions. But,
okay, thank you. I think we are moving towards the kind of questions that could be discussed with great benefit in the bar, and we may be getting close to that time. But perhaps one final question at the front here.
Hi, it's Yang from IBM. So, if I may allow to take the audience back to the key question here, it's not something I want to ask, but rather to validate. I like the smart dusk idea. But just to circle back all the questions asked from the beginning to the end, there is a concern about security in terms of data inception, and maybe the data will be stopped for security reasons, intercepted by something. right? And then you mentioned about using smart device we use on a daily basis to transport this kind of data, transmit them into a data center, as you just mentioned earlier. So to me, this session is almost like a starter, because you already have the idea of the dust, where to collect the data. But what we need to think about more is, through this collection, how to use the device where they have computing powers to actually package this data securely and then send them on to the destination where we can use AI and machine learning to do the actual stuff. So I hope that we can hear a lot more through this forum, not just about the data collection, but the later on steps that we need to do to actually make the real smart city. So is that really a trend? You have the starter now, but we need to connect all this together.
No, it's just my research. This is where when you do research, you do it narrow, deep, right? You do real focused, right? Mm-hmm. Then my colleagues in the data, data analytics, stats, big data centers, they do all their research in those parts. And then there's people who are not in the research world, people who do actual real things in cities and so on. They're building the end-to-end, right? But for me to make sure the bit that supplies the data to all those analytical systems and so on up the pipe, I have to make sure that that's reliable. My job is to make sure that's reliable, and I've specialized in that. So that's why this talk is at that end. Mm-hmm. Those other bits, that's for maybe next year's Turing Talk.
I look forward to the rest of the bit as well, because certainly there needs to be like points connecting together to see what smart city really like.
Yeah.
As in, this topic is very specific, of course.
It is.
Yeah. Thank you.
Thank you, Simon. Maybe I could take the opportunity to agree with you very much. As someone who works perhaps at that slightly higher end, it would be great, I think, to have a future talk here, which is more about those applications. Can I ask Julie or anything else that you'd like to say or reflect on while you have the opportunity here before I draw things to a close? Nope.
I just think it's a very interesting topic right now. I think the government is talking about things like cyber-physical infrastructure, which is taking these kinds of little devices and getting more information and digital twins and stuff. So these are the kind of trendy at the moment. But I think all this systems of systems and modeling and so on is very interesting on so many levels. And I think a lot of people will get more engaged. And okay, I'm down at the sensor end, but there's a whole lot of people beyond the sensor end. Yeah, so it's an interesting topic, and I think you'll see more focus on it.
Okay. Thank you. Well, I'm sure you'll agree it is indeed a very interesting topic and illuminated very nicely by the two speakers this evening. So perhaps we could thank them again in conclusion. Could I thank you all very much for joining us this evening, and for those who have been joining us online. For those of you who are in person, please do join us if you can for drinks after the talks, which will be in the registration area where you came in. There'll be an opportunity there to talk to the speakers and, of course, to network with one another. Could you please look out for our questionnaire about this event and to give feedback on the events this evening. And if appropriate, I'm told that will also include a link to download to your CPD certificate if you would need that. So again, thank you very much. I wish you a good evening, and if you're departing straight away, then a safe trip home.